So in this lecture, we're going to look at denial of service attack. Another classic form of attacking a computer system where we don't attack the confidentiality or the integrity, but the availability of a computer system. So that's the third letter in the CIA. Okay. And we'll see that there are many forms of denial of service attacks, and that this is still an active research area also. And I'd like to point out that some of the things that we discussed in the previous videos also contain elements of denial of service attacks, or indeed can be used as denial of service attacks. We've seen that the XStorms can be used as denial of service attacks. The termination of connections can be used as denial of service attacks. The ARP spoofing attack, where we send all of the traffic in a local area network to a non-existent MAC address, is a denial of service attack, and so on. Okay, so sometimes it's hard to create clear boundaries between different types of attacks. Now we're really going to focus on denial of service attacks proper, and we're going to start with some of the classic attacks, just like we did in the TCP hijacking case. We look at some classic attacks, and one of the most classic attacks uses the IP fragmentation that we alluded to in the previous video. So let's briefly recap what IP fragmentation is all about. When a datagram is sent over a network a connection, right? So it may be that from one hop, from one link to another, the maximum transfer unit changes, right? It becomes too small, and the large packet can no longer be transmitted over that new link. In that case, the datagram will be automatically fragmented. It will be partitioned into smaller fragments so as to fit the MTU of the new link. Okay, and the fragmentation happens either at the source or somewhere in the middle of the network, at the routers. Okay, the defragmentation, so the reassembly of the packet, only occurs at the very end, so at the destination. If the datagram has a do not fragment, the DF flag, right, a do not fragment flag set, then whenever a fragmentation is needed, an ICMP error message will be sent back to the originator. Now, we've seen all of this in the previous video. Now let's have a look at what this means in detail. Okay, so fragmentation uses a number of fields in the IP header. And one of them we've already seen, the IP ID, the IP identifier. Okay? All the fragments of an original IP datagram will have the same IP identifier, the same IP ID. Okay, and in this case we have an example of a datagram that has a length of 4,000 bytes. Okay. And it has a frag flag that's set to 0, so it's not fragmented yet. And it has an offset of 0, which means that the first byte in this datagram is indeed the first byte in the packet. Now, if we encounter another type of network, say a classic Ethernet with 1500 byte frame length, then we need to fragment this 4,000 byte packet into 3 fragments. In this case, we fragment this into 2 fragments of 1500 bytes and 1 fragment of 1040 bytes. Now, you may look at this and initially think, wait a minute, this doesn't add up, right? So if we add 1500 to 1500 to 1040, we actually overshoot the 4000 length that the original datagram was all about. And if you start thinking about this a little bit longer, you'll realize, oh, I know what this is. We still have 2 additional IP headers, right? So we need to add these IP headers, and each of the IP headers is 20 bytes. So we have 2 additional IP headers of 20 bytes, which is the additional 40 bytes. Okay, so we have 3 fragments, 2 of 1500 bytes and 1 of 1040 bytes. And they all have the same identifier, all have the same IP ID. Okay, and the first 2 fragments have their frag flag set. So the frag flag essentially just indicates there are more fragments following. So in the original datagram, there are no more fragments following. So this is the last fragment. In fact, it's the only fragment. But here there are more fragments following. Here there's also another fragment following, and only in the last one the frag flag is set to 0. There are no more fragments following. Finally, we indicate the offset of whatever is in this particular fragment using the offset field. Okay, so the first fragment, the bytes in the first IP fragment will start at offset 0. Okay, the bytes at the second fragment will start at offset, wait a minute, 185. We said we send a packet of 1500 bytes, and then there was a header also. How come we don't arrive at 1480? Why is this 185? Well, the reason is that the offset counts in multiples of 8. Okay, so 185 is 1480 divided by 8. So it is indeed the offset that we expect. So the next chunk of bytes will be placed in a buffer. So whenever this arrives, it will be placed in a buffer at offset 1480. Okay, and the next set of bytes, the remaining bytes, will be placed in the buffer at an offset of 8 times 370. Okay. Okay, so this is how the fragmentation works. And if we send a packet of, say in this case, an ICMP echo request, what we can do is actually specify a very large echo request, so a large amount of data that is being sent. And we see that the first ICMP echo request gets sent from our source to our destination. It's an ICMP echo request, and it's a fragment with an identifier, and it has, in this particular case, the first one has 1480 data bytes, and they start at offset 0. The next fragment with the same IP identifier is also 1480 bytes long and starts at offset 1480. The next one starts at offset 2960. The next one at offset 4440, and so on. So until we reach, a very large offset. So a maximum IP datagram is 64 kilobytes. So we can go to tens of thousands of bytes. Okay, so that's how fragmentation works. Now, one of the classic denial of service attacks that we've had in the past and that no longer works today is known as the ping of death. It's the attack that is making use of the fact that the offset of the last segment can be such that the total size of the reassembled packet is bigger than the maximum allowed size. So if you only allocate enough memory for the maximum allowed size according to the protocol, and you're able to specify a length by means of these offsets that actually exceeds that maximum allowed size, you get a problem, right? So you actually have to store more bytes than would fit in the buffer that you allocated for this. And this is known as a ping of death. And the ping of death causes a kernel static buffer to overflow, or it caused, because it's a long time ago, and that caused a kernel panic. So here is an illustration of this, and this time we're starting from the top. We're sending again an ICMP echo request, and the first fragment contains 1480 bytes again, starts at offset 0. The second one, 1480 bytes at offset 1480, 2960, 4440, and so on. And we send more and more and more, and then at some point we get to this fragment that contains 398 bytes, and it starts at offset 65, 120. Now this is problematic because, like I said, the maximum IP datagram is 64 kilobytes. In other words, 65535 bytes long. Okay. So, but if we now do the math here, we have 65,120, that is the offset. We add to that 398, okay, 398. That's 65,518. So we're getting close to the maximum datagram size. But now we also have the header, right? There's an additional 28 bytes of header. So we arrive at a size that is 65,538, which is larger than the maximum allowed IP datagram. And hence, if you only allocate this much buffer space, it will not fit. And you will actually corrupt something. And in this case, it caused a panic. The ping of death. You could just send ping requests, ICMP echo requests to various hosts on the internet, and you would simply cause them to crash. It no longer works today, but interestingly, we recently discovered, or by now it's a little while ago, but I don't think it's been fixed yet. So-called page of death, which crashes many browsers. Okay, so regardless of the browser, just that one page would crash. I don't want to tell you about that because it's something that we haven't published, we haven't fixed yet. But it's an interesting phenomenon. So just a simple GET request would crash you. Okay, but I will not tell you about it. Another really classic denial of service attack is known as SYN flooding, also known as Neptune attack. And the idea is, again, extremely simple. You start by setting up TCP connections, so initiating your TCP handshake. And then the victim replies with the second phase of the TCP handshake, which is to send the SYN-ACK segment. But then the attacker doesn't follow through. It doesn't send the third phase of the TCP handshake and leaves the server dangling. Okay, so since you don't send this third phase of the TCP handshake, you don't have to worry about the reply of the server being visible to you. You can just spoof the TCP SYN source IP address, because you're not going to send the third phase anyway, so you don't care about the sequence numbers. So this makes it all really simple. So the source IP address of the attacker can easily be spoofed since you don't need a final acknowledgement. Now, the host, a server, can keep only a limited number of TCP connections in this half-open state. After the limit has been reached, it cannot accept any more connections, and it's essentially dead. There are many ways in which you could solve this. You could try to filter out some of these bad packets. You could increase the length of the half-open connection queue to be able to absorb more. You could reduce the timeout that you require that you set to cap the amount of time before you can receive one of these acknowledgements on your SYN-ACK. You can also drop some half-open connections when a certain limit has been reached, and then you get new requests for the connection, so you can still accommodate a new request. You can limit the number of half-open connections from a specific source, right? So there's all sorts of not so clever things that you can do, or you can use TCP SYN cookies. And nowadays, TCP SYN cookies are really quite popular. Okay, and it's a fairly adequate defense against TCP SYN flooding. Okay, let me tell you about TCP SYN cookies. Okay, TCP SYN cookies go back to our initial sequence number generation. So the initial sequence number is now generated in a very special algorithmic fashion. The TCP initial sequence number consists with SYN cookies consists of multiple parts. So it's essentially 3 parts: the first 5 bits, the next 3 bits, and the remaining 24 bits. So it's a 32-bit number, and the first 5 bits are special, the next 3 bits are special, and 24 bits are special. So the first 5 bits we use to have a counter. We have a 32-bit counter that increments every 64-bit seconds, and whatever that value is, we calculate that modulo 32, right? So because we only have 5 bits, and that's what we put in those first 5 bits. And it gives an indication of the freshness, right? So if we receive some, as we shall see later, when the server receives some SYN-ACK, some acknowledgement, some third phase of the TCP handshake, it will check whether or not this is a plausible datagram, a plausible third phase of the handshake, because it's recent, right? So that's roughly how that works. Okay, so 5 bits for the counter. Then there is 3 bits that encode the maximum segment size. So normally the maximum segment size can be anything, right? So it could be an arbitrary value, but now we only have 3 bits to encode the maximum segment size. And the way that works is that you basically have 2 to the power 3 is 8 different preset values for the maximum segment size. Say it could be a very large one, some intermediate ones, and a small one perhaps, right? Who knows? But there's a maximum of 3 maximum segment sizes that you can encode in those 3 bits. And then the remaining 24 bits are a keyed hash of the full counter, right? So that we had the top 5 bits so the first 5 bits contain the counter modulo 32. Okay, but we have in the 24 bits we have a keyed hash of that counter, the full counter, and the source, destination, IP addresses, and ports. Okay, so this is something that we can obviously use later to verify. Now, why do we pick such a really complicated way of calculating an initial sequence number? Well, what the server is going to do whenever it receives a TCP SYN, so the first phase of the TCP handshake, what it's going to do is it's going to accept that, calculate such an initial sequence number, and send that back and forget about it, right? So it means that it doesn't keep any complex administration as to the half-open connection that it has accepted. It will forget the half-open connections. And only when the third phase of the TCP handshake arrives, right? So the third phase coming back from the client, then it starts remembering what this was all about. And then it creates the state that corresponds to it. So let's see how it does that. Okay. So a server, whenever it uses TCP SYN cookies, all it does is send back a SYN-ACK, right, with this initial sequence number. And when the server then receives the ACK that corresponds to that SYN-ACK, it will simply execute a number of checks and then reconstruct the corresponding state. Okay? So it will check that the secret function, so the keyed hash, works for a recent value of the counter. So it's a fresh response. It's something that was in response to a SYN-ACK that the server sent recently. Okay? Helps to defend against replay attacks, really old ones. Okay? And then it rebuilds the SYN queue entry as it would have existed if it had kept state at the time. Okay? And it can easily do that because it knows the encoded maximum segment size. It's in there, right? And it also remembers its own initial sequence number because that is essentially encoded in the acknowledgement number received from the other side. Okay, so it can rebuild this SYN queue entry, and therefore it can just simply forget about the half-open connections, and you can no longer do this kind of attack. You can no longer exhaust the number of half-open connection entries because there are no longer any half-open connection entries. There's some drawbacks. So your server sequence number grows a little faster than normal. The maximum segment size is limited to only 8 possible values, and you can no longer send any data whatsoever with the initial SYN. Just to illustrate what's going on is you have a client that sends a TCP SYN message with a sequence number for the client. The server kind of forgets about the half-open connection, but sends back a SYN-ACK that contains, this 5-bit top of the counter value, the maximum segment size encoded in these 3 bits, and a hash of this counter plus the 4 tuple that we looked at. And then when the client was legit and really wanted to set up a proper connection, right, a full connection, it will have to send back an acknowledgement to the SYN-ACK, and the acknowledgement contains obviously the client sequence number, but also the server's sequence number +1. Okay, and the server sequence number +1. So if we simply subtract 1 from that, we get this value again, right? So we again have the hash, we have the 5 bits of the counter, and we have the maximum segment size. So we can verify that this is correct for a recent value of t, and then we know the maximum segment size, and we also know the sequence number. Okay. Now those are classic denial of service attacks today. Now let's have a look at what we can do in denial of service today. And we have a number of different kinds of approaches that attackers can take in the modern attack. And the first one I want to go through is the low volume attack. So the SYN cookies, the SYN flooding attack consisted of a lot of packets that needed to be sent, right? So you had a lot of TCP SYN segments that would fill up the half-open queue. So you bombard the server with lots of requests. There are lots of other denial of service attacks that simply bombard the server with data just to make it unresponsive to other requests. The way Kevin Mitnick took out the server was by a high volume attack. Now, in contrast, the ping of death was a very low volume attack. It only contained a single packet that created problems. So in this case, it triggered a kernel panic. But there are other low volume attacks that actually use some resource, so a disproportionate amount of resources simply because of the way the server processes certain requests. Okay, so let's see, these are the low volume attacks. There are certain attacks that exploit the fact that the server has to maintain a certain amount of memory resources associated with the open connection. For instance, memory for the socket descriptor, process or thread to manage the connection, memory associated with the data in the TCP stream that hasn't been acknowledged, and you may try to exhaust all of that. But you can also make this more advanced and use the algorithmic complexity. So if your server is doing something with the request data and it has some worst case behavior for extreme values of that attacker's data, you can make use of that. For instance, if the server allows you to send a regular expression to be evaluated on a data set, for instance, that's just what the server does. Some search it does in a database on the basis of a regular expression. You can make that regular expression extremely complicated, so it takes a very long time to evaluate. Sometimes some regular expressions can be much more expensive than others. Okay, so that's a worst case behavior, and you make use of the fact that even the small connection, so the small request, may take a very large amount of memory, very large amount of CPU time, or whatever resources that you want to exhaust. There are some practical examples of low volume attacks, and one of them is Black Nurse, which exploits a vulnerability in a Linux-based firewall, consumes a lot of CPU cycles to process destination unreachable, protocol unreachable ICMP messages. So if you know that this is the worst case and it's really disproportionate in the amount of resource consumption, that's what you're going to be going for. Likewise, there's an Apache range header attack, which exploits a performance bug again in Apache Web Service that exists in handling the HTTP range header. Now, these are complexity attacks that simply take very little data and still, take out a lot of resources. On the other hand, we can also send, huge amounts of data. Let's take the, extreme other end of the spectrum, and that is not just send, a lot of packets to fill up a TCP half open queue, but let's say, massively bombard this server that, whatever it is trying to do, it will never be able to process anything anymore. And there are different ways in which we can do that. In the past, we've actually investigated a number of denial of service botnets, and these are, somewhat older ones, Dirt Jumper and DoS, that we reverse engineered and looked at what they were doing, how often they attacked, and it very much varied, right? So the number of targets per day for Dirt Jumper was in the, maybe between 50 and 100 on average, whereas DoS wasn't used very much, right? So it was only occasionally active, at least in the time when we looked at it. And they were different in complexity. So Dirt Jumper was multi-threaded, but it only could do HTTP attacks, so only sending GET and POST requests to a server, whereas the DoS one was also multi-threaded, but it had a wide variety of denial of service attacks. So it could do TCP, UDP, HTTP, etc. But it wasn't used as much, at least in the time when we looked at it. Okay. And we try to measure how effective they are, right? So we try to see how often they succeed in at least, making the target suffer. And suffer could be that we can't reach it anymore, or that it slows down, or that something has changed in the DNS handling, right? So you make the DNS mapping point to maybe something special, or something else, right? And the something special, by the way, if you change the DNS mapping, could be mapping it to a loopback device or so. Anyway, so on average, we find that in some 65% of the cases, there was a very noticeable effect on the victim. Now, by the way, measuring this is tricky, right? Because you want to do this ethically. You don't want to constantly start probing the victim of an attack, because then you might essentially be participating in the denial of service attack. So you don't want to send too much extra data to avoid bombarding the poor victim even more. Okay, and what we did, by the way, just to complete the story here, is we reverse engineered these these pieces of malware, and then we created our own versions of Dirt Jumper and DoS, and we made it participate in the botnet without actually doing the harmful things. So it only would listen to the communication, so we would know who the targets were that were being attacked, and then we would, very carefully check whether or not that target was affected by the denial of service attack. So that's what we did. But these were not very massive denial of service attacks. In contrast, the attacks that were launched by Mirai, the Mirai IoT-based botnets, and Mirai means future in Japanese, apparently. That was very high volume. So in that case, the amount of traffic that we've seen exceeded 1 terabit per second. That's the first time I'd heard of a denial of service attack exceeding 1 terabit per second. Okay, this is in 2016 already. And the kind of devices that were used here for the denial of service were, surprisingly perhaps, really low-end devices. This was the Internet of Things attacking some, larger systems. It was the Internet of Things consisting of cameras, or I don't know, a TV receiver, or routers, printers, and even more cameras and printers. So it was the IoT, the smallest devices that you have, that were being used for a massive denial of service attack. In those days, a terabit per second denial of service attack was unheard of. Okay, and it's a problem because these IoT devices, there are many of them, and they increase in numbers very rapidly. And all of them may be, relatively low end, but if you combine the amount of traffic that they can generate, it actually adds up to very high amounts of traffic. Moreover, these are IoT devices such as security cameras and refrigerators and so on. And people don't, spend a lot of time checking what they're doing. They don't check whether or not they might be hacked. Typically, the security on these devices is not very mature to begin with. So this IoT, the IoT is a huge threat for these kind of okay. And the way Mirai worked was it was a relatively complex procedure. So there were bots that could actually participate in denial of service attacks. There was a command and control server. So C2 means command and control, sometimes also written as CNC. So it's a command and control server. There were obviously victims. So there was a denial of service victim here. There were victims that would be scanned. There was an attacker sitting here. And then there was malware that was distributed to even more victims and so on. So the attacker connects to its bots, to the bots that it has infected, the machines that had been infected, via a command and control server, okay, and also to the report server. And it would do so via the Tor onion routing system. So Tor allows you to use onion routing, so multiple layers of encryption to hide your own identity, right? To connect to these command and control and reporting server. Okay. And it would sell denial of service functions to users, okay? And they would send their attacks via some API that they've been given. Okay. The command and control server is in charge of launching the denial of service attacks that would originate from the individual devices under control. So it would publish essentially the attack command, which would be picked up. Okay, it would be picked up by the bots, and they would then all launch a massive attack on some poor victim here. The command and control server has to be protected, so it would change its IP address over time. So it would move around to make it harder for people to take it down. Okay. Moreover, the reporter service would then report on how successful the attack has been. And the other thing that the reporting service would do is so the command and control server would, for instance, tell the bots not just to do denial of service attacks, but also to launch scanning attacks to see which other victims are vulnerable. Okay, so for instance, there's a camera here or a refrigerator there, and it turns out that Mirai is able to infect them. So they scan them to see if they're infectable because they have a default username or password, or it's something that it's really easily maybe doesn't even have any username or password. Anyway, so it gives you a report on which machines might be possible victims, and then we log into these devices to infect them. So there's loaders that log into these devices to instruct them to download the Mirai malware, and then you become a bot also, and you're under control of this command and control server, hence the attacker, and you're participating in denial of service attack. Okay, so it's a fairly complex but elegant and nicely partitioned infrastructure. Okay. And like I said, terabit per second, can't argue with that. Okay, I think I mentioned that. But having millions of devices, which is what Mirai had, is only one way of generating a lot of traffic. A completely different approach is to use amplification. And amplification started with a Smurf attack, which no longer works today. It's an old school amplification. And the idea is quite elegant, right? So you want to attack some victim over here, but you're not going to send that victim any data from your own machine. Instead, what the Smurf attack did was it would send echo requests from, 128.111.41.10, which seems to be the victim. Okay, it seems to be the victim. So you're spoofing echo requests, and you're sending that to, a lot of machines here. In fact, you're sending it to all of these networks. So it's a broadcast message, 255. So it would be broadcast on these local area networks. Can't do this anymore, but it would broadcast on this network, and then all of these machines would receive that message and reply. Right? It's a ping request. So you echo that with an echo reply. And all the replies would be sent to what looks like to be the source of that ping request, which is 128.111.41.10, one in here also, and here also. That means that with 3 packets sent to these local area networks here, we already generate a huge stream of replies to the poor victim. So we're getting a huge amplification of the data that we send into the network, as our Smurf shows here. Okay? And like I said, it no longer works, but the principle is still there. Okay? Amplification today is using something slightly different. So it's sometimes also known as distributed reflective denial of service, but most people simply call it amplification. And the idea that it builds on is that, especially if you're using UDP, it's an easy thing to do. It builds on the fact, the key concept here, that a reply is often much larger than the request. So if you're able to send a really small request and then receive a huge reply, maybe multiple packets long, you're amplifying the data that you're sending into the network. Okay? And if you want to know more about amplification, you should have a look at the amplification hell paper, or the return from amplification hell, or whatever it's called, both by Christian Rosso at the time, who used to be a PhD student at the Vrije Universiteit, but now is a very successful professor at Saarbrücken at CISPA. And what he showed was that you can send, for many protocols, you can send small packets and then receive a huge amplification. For instance, you can use these types of protocol, network service protocols, such as a simple network management protocol, or the network time protocol, or DNS, right, core service in the internet, and a bunch of other. You can use some legacy protocols, such as the quote of the day protocol or the character generation protocol. You can use peer-to-peer protocols, such as BitTorrent or Kademlia. You can use game engines, such as Quake 3 and Steam, and you can use other botnets, right? So here it's not actually the botnet that's attacking you, but you using the botnet to attack somebody else, right? So the botnet just happens to be convenient there. And all of them have this property that small requests can elicit large replies, okay? And that it's UDP, so you can very easily do this. You can spoof the request, and the reply will be sent to whatever spoofed IP address you provide. Does that actually lead to a lot of traffic? Well, it depends on your protocol, right? So in this table, which was taken from the paper, we see a lot of protocols here, so the protocols of the previous slide, and then we have 2 sets of results, the byte amplification factor and the packet amplification factor. Okay, and for each of them, we show different categories. So across all of the servers that we find on the internet, or if we only look at the top 50%. Oh, actually, we only do this for the byte amplification. For the all of the servers that we find, top 50% of the servers and the top 10% of the servers. So for instance, right, so the network time protocol has a byte amplification factor of, across all the NTP servers that they found at the time on the internet, a byte amplification factor of 556, which meant that for every byte that you would send to the NTP server, you would receive 556 bytes back. Okay, but if you started looking at the top 10%, so certain NTP servers did even better than that, right? They were able to send even more data back. So here, the top across the top 10%, and we're still talking about thousands of servers, right? The top 10% had an amplification factor, a byte amplification factor of over 4,000, right? So for every byte, you would get more than 4,000, in fact, 4,670 bytes back. Okay, so that's a huge amplification factor. And that meant a packet amplification factor of over 10. For every single packet that you would send, you would get 10 packets back. Okay, that generates a lot of traffic, certainly if you have a lot of these NTP servers in the internet. And the problem with NTP, so NTP was clearly a very good one to use here. The problem with NTP is that it has a specific command called monlist, which allows you to send a huge amount of a reply that's huge. So you actually get a huge amplification on that particular command for that particular server. And we'll look at monlist in one of the next slides. Is there anything else that I wanted to say about this slide? I don't think so. Okay, so here's the NTP monlist command. What does monlist do? Well, you can use that to query the NTP server for the last up to 600 hosts that have last contacted the NTP server. Okay, so you send one small request in a UDP packet, and you will get a list of all the servers that have contacted the NTP server. Okay. Now, this is cool for an attacker to begin with, even if you don't want to do a denial of service attack, because it might be used for reconnaissance also. You're actually harvesting these IP addresses. Okay. And it's clearly not a very cool thing to have. Who would actually use this constantly? Why is this essential to have on the public internet? And the fix was to remove much of this. Okay, so the amplification attacks are quite effective also. We've seen hundreds of gigabytes attacks as early as 2013. Okay, so that's still huge amounts of traffic with these amplifications. Okay. And the main protocols that were used were the network time protocols in practice, right? So the network time protocols and DNS. Because DNS also has a decent amplification factor, and that was used. There are some that were also used. So the legacy protocols, Chargen was used, and there were some other ones, but it's by far dominated by the network time protocol and DNS. The most impressive attack that we've had, at least in recent years, was the memcached attack, which is also an amplification attack. Okay, and it's caused by memcache daemons, right? So memcache servers that for some reason were exposed on the public internet. It's unclear why anybody would want to do this, but anyway, so these machines were on the public internet, and these are key value stores, right? So you can just ask with a small query and get a huge reply back. And by doing that, the attackers were able to generate a record-breaking 1.7 terabits per second in a denial of service attack. Okay. I have no doubt that the record will be broken at some point, but these are fairly impressive attacks, so amplification does work. Okay, so we've now seen the algorithmic complexity attacks, or the stealthy attacks, low volume attacks. We've seen, huge volume attacks, and now let's look at, even stealthier attacks in that it becomes harder to determine that the denial of service attack is taking place to begin with. Okay, so now what we're going to look at is something that hasn't been seen in the wild, as far as I'm aware, but has been shown in research to be effective. And it's an attack where the attacker tries to do a denial of service attack without making anyone aware of the victim being attacked. So, and to do that, you do not attack the victim directly, but rather you attack other sites. Attack sites that share a link, so a bottleneck links with the victim. Okay? And you do this in a stealthy manner. So the attacker sends only a tiny flow of data. But you do this from a large number of machines. You have a large number of machines, each sending only a very small trickle of data. And each of those machines is only active for a small amount of time. So maybe your machine is working with this small amount of data for 1 minute, and then I take over, right? So you go down, you terminate your connection, and I take over and start sending data again for only a few minutes. And then maybe somebody else takes over, and then you take over again. So all of us are active only for short amounts of time, and with only small streams of data. So that makes none of our streams look suspicious. Okay? They all look like, legitimate low volume streams. Moreover, none of us has attacked the actual victim, but still it's the actual victim that suffers. So that's the idea. So we have, and that's the assumption, a large number of machines, say a botnet, and we want to attack some servers in here, maybe one or multiple servers in a target area. And a target area could be, I don't know, an organization. It could also be a city. It could be perhaps even, the researchers showed that they thought they could do this even for, say, the east coast of the United States or the west coast of the United States. I forgot which. So huge amount of a huge area. Okay, so and all of these bots that we find on the outside here are attacking not the victim, but they are attacking bottleneck links towards the victim. Okay, so these links that we see here, the red links, by connecting to so-called decoy servers. And the decoy servers are not the victims, but they together surround the victims by means of all the path towards the victim. So they all share bottleneck links towards the victim. And if we manage to clog up all of these bottleneck links, it also means that the traffic towards the victim is also clogged up. You cannot get into that. Okay. So essentially, you are targeting this by choking all of the path, all of the roads into your area. It's like you're choking off a city by blocking all the roads towards the city, even if you don't block them at the city itself, right? So maybe you're sending traffic not to the city, but traffic to the villages close to the city, right? Essentially, they use the same roads that the traffic towards the city would use, and hence would also block off the city. It's that kind of attack. So here's what you would do as an adversary. You would use trace data from a number of vantage points to discover what the routes are to the victim, right? So to the target area. Okay, and these routes should be ideally persistent. So you don't want to have the route flapping that you might otherwise have. And then you're going to look at what are the best links to choke off, right? So you're going to look at what the flow density is, how many of the flows from different vantage points go over a particular bottleneck link, right? And then that has a high flow density, and you're going to target select the targets on the basis of how much will they actually choke off the victim area. Okay, so do a flow density computation, and then you do a target link selection, and then you're going to send traffic in this stealthy manner to the decoy servers close to the target servers. So this are the decoy servers, and this is a target area that is never really targeted, but is still choked up. Okay, because the bottleneck links towards these public these target servers are blocked. Okay? And they're blocked in a stealthy manner, so with low volume streams that are only active for a limited amount of time. And together, combined, we have a very stealthy attack that is hard to detect. Okay, so we've seen multiple types of denial of service attacks. I'm sure that we'll talk about denial of service attacks in later lectures also. But this is all that we wanted to say in the topic of network security. All right, so now let's move on to different kinds of attack.